All right, first thing I want to talk about is an important number right here, the number 3. 3 is the number of times I've restarted this video because, well, who would want to bother with writing a script or anything nice like that? So I want to talk today, let's talk about a closed container right here. And this closed container has water in it, okay? Wow, it's closed, it's a water bottle. It's stronger than a water bottle for what we're about to do. And let's say that I know that the temperature inside this thing is 135 degrees Celsius, okay? And I want to know what the vapor pressure inside that closed container is going to come out to be. All right, well, there's a formula for that, thank goodness, because yeah, you wouldn't want to experience it firsthand, like, face pressure test, open it up, burn your face off, I don't know, whatever. Okay, so here's the formula. I know I'm not really a funny guy all the time. Sometimes I get lucky, though. Okay, so here's P1. Okay, so that was beautiful. All right, I'm going to take the natural log of P2 over P1 is equal to the heat of vaporization. If you've done Born-Haber stuff, then you'll understand what I'm talking about here a little bit, but you can go back and look at that video too when I talk about enthalpies. This bottom number here is going to be R, and that's an atmospheric pressure constant, and we're going to see later that it's important that you choose the right units for that one. And then over here I'm going to say 1 over T1 minus 1 over T2. Now, you might see this in different forms because you can rearrange things, whatever, that's fine. But we're going to do it this way this time. Okay, so now you say, I know this temperature, and another number that you probably need, and you'd get, in the back of your book or something like that, is this number right here. Delta H is equal to, and this is the heat of vaporization I was talking about up here, is equal to 40.7 kilojoules. Okay, and that's per mole. All right, now I think I have enough to get started. First of all, well, you say I only have one pressure, right? Actually, I don't even have a pressure, I just have a temperature. How am I going to do this? Well, as it turns out, you have more information than you think, especially when you're dealing with water, because first of all, you know the temperature of water when it boils, right? So, and you know the pressure at which it boils. This is pretty easy, so let's look at it. That's going to be, let's just write it out. Natural log of pressure 2. That's what we want to know. What's the pressure when we hit 135 degrees? Well, okay. Don't know pressure 2. Pressure 1, well, let's go with the boiling point of water, and that's going to be 1 atm for the pressure, and on the other side we'll use 100 degrees Celsius, and that'll work out just nice. All right, that's equal to 40.7 kilojoules per mole. Okay, and that mole's an important clue for which value of R you want to use here. It's 0.0821. Is it that? Is that what I want? Yes, it is. Okay, so this is going to be in liter ATMs. That's 1 ATM here, so don't get that confused. Liter ATM per K-mole. And actually that should be a capital K because that's Kelvin moles. Okay, so Kelvin times, and this is liters times. All right, so that's this value here. The next part we're going to plug in is going to be 1 over, let's scoot over a little bit, 1 over T1. T1, well, T1 is the temperature at which water boils, so we're going to say 100 degrees Celsius. Oh, wait a minute. These units are in K, so we're actually going to want to say plus 273. And we're going to subtract from that 1 over temperature 2. And temperature 2 is, well, 135 plus 273. I've gotten lazy about units. These should both be in Kelvin, right? Once the math is done here. It's a capital K, and same for here, and there wouldn't really be any degrees. degrees. Okay, no degrees Kelvin, no such thing. Okay, so now we can just start simplifying. I'll get out my fancy calculator here, and let's take a look here. First of all, I'm going to say the natural log of P2, and this would be an ATM, these cancel out, right? So is equal to, and let's see, first of all, 40.07 kilojoules per mole divided by 0.0821. I wrote that down. I'm wrong. Sorry. This should be 0.821. Yeah. I've become amazed at the number of numbers I've had to memorize and have done so semi-successfully up till this point. All right. Divide, and I get 488. Now, depending on the class you're in, you might have to use a pretty chintzy calculator. I know it's true of my Gen Chem 2 class, and well, it can just help out to write down the steps as you go so you don't lose your place because you don't have a fancy graphing calculator anymore. Okay, so that's 488. I'm not going to worry about units for right now because I just want to get to the answer. You can check for yourself to see that the units work out. Okay, now I've got 100 plus 273. Oh, I said 110. Crap. Well, I'll put that in. We'll switch them. And we'll drop that, and I'll say 100. Got it? Okay, good. Plus, and I want the reciprocal of that, so I'll press my handy reciprocal button. And let's do the next one. 135 plus 273. That's 408, and I want the reciprocal of that. And that's that big hairy number. We're not really worried about it that far out, but we'll use it anyway. And now I'm going to subtract the one I just got from this one, and that gives me this value here. And that is where I'm going to start doing a little significant figure rounding just so it fits. 2.30 times 10 to the negative 4th power. Okay. And now, I think we just multiply those out and we'll be good for the next step. So multiply that out and I get that the natural log, I want a new color, that's getting really boring. Alright, here we go. The natural log of P2 is going to be equal to 0.112. Okay. And so the way I'm going to undo that natural log so I can find out what P2 is really worth is I'm going to say, where's my button here? Sorry, I've been switching calculators today. I'm going to go for the exponentiate button, and it'll give me this value. All right. I've been working in Tor all day, so that number kind of caught me off guard, but that is what we wanted. So P2 is equal to 1.12 ATM, and that's the final answer for our problem, and that's 2-point pressure problems. Just to review, again, if you have one temperature and you have the heat of formation and you have R available, and you know the boiling point and pressure that is normal for that substance, then you can pretty much work your way to any pressure inside a closed container. Thanks. Good luck on your tests and whatever, or yeah, see you later.